Our weekly interactive math reviews for Math 1332 and Math 2412, presented by Yvette Chuca, Ruben Carrizales, and Albert Isasi. This session will be recorded so that you may come back to it later. Also, it is recorded so others may have missed out on today's events will be able to come back and watch it. So now at this time, please mute your mics for best sound experience. Otherwise, the feedback could interfere with the information we'll be sharing today. Without further ado, here is Yvette Chuca.
Hello, everyone. So we're going to be covering for Math 1332, the counting principle, permutations, and combinations. And so we'll get started with that. So for the counting principle, this is from section 12.1. And so the counting principle is a tool that helps us to figure out how many possible outcomes we have. So for example, if you were to flip a coin, we know if it's a fair coin, we know we can have either a heads or a tail. So those outcomes, we can list them as a set of H for heads, T for tails. So we say that there's two possible outcomes. If you have a dice and you roll the die, how many outcomes are there if it's a regular six-sided die? And we use the term regular because, you know, we are assuming that these are fair dice. So if we were to roll these, let's see, what do we get? So the outcomes would be that when you roll the dice, you could get a 1, you could get a 2, you could get a 3, a 4, 5, or 6. So we say that the outcomes can be listed as 1, 2, 3, 4, 5, 6. So we have 6 possible outcomes. Okay, so here's another one. List and then count the number of different outcomes that are possible when one letter from the word Tennessee is chosen. Okay, so let's go ahead and do this one. So the possible outcomes, if you choose one letter from this word, you can get a T, you can get an E, or an N, or an S. The other ones are repeated there, so we just need to write it one time. So we say that there's 4 possible outcomes. Okay, so we're going to be using different ways of counting, and you're going to see some definitions that we're going to also be talking about, which you're going to use for the rest of this chapter. So an experiment is an activity with an observable outcome. So for example, flipping a coin or rolling a die or choosing a letter, those are all considered experiments. And the set of possible outcomes, we call them sample spaces. So the sample space of flipping a coin was HT. The sample space of rolling a die was 1, 2, 3, 4, 5, 6. And the sample space for choosing a letter from the word Tennessee was TENS. Now, an event is one or more of the possible outcomes of an experiment. So flipping a coin and having a head show on the face when you flip it, that would be an event. Or rolling a 5 when you roll the dice, that would be considered an event. And so an event is just a subset of the sample space. Okay, so if, for example, here you have 1, 2, 3, 4, 5, 6. If you get a 4, then that's called an event. So an event is one or more of the possible outcomes. Then we're going to have a single stage experiment. This is when you have an experiment for which there is a single outcome. And then we also have experiments that have 2, 3, or more stages, and those are called multi-stage experiments. So here's an example. 2-digit numbers are formed from the digits 1, 3, and 8. Find the sample space and determine the number of elements in the sample space. So you have these 3 digits and you want to form a 2-digit. So for example, 13 would be a 2-digit number. So we can figure out how many we have. One strategy to keep track of our sample space is for us to use a table. Okay, so here's a table. So we have the numbers 1 through 8. So one outcome here could be that we get a 1, 1. We can have a 1, 3 or a 1, 8. We can have a 3, 1, a 3, 3, or a 3, 8, 8, 1, 8, 3, or 8, 8. So these are all sample spaces. So the sample space is going to be 1, 1, 1, 3, 1, 8, 3, 1, 3, 3, 3, 8, 8, 1, 8, 3, and 8, 8. So there's 9 2-digit numbers that can be formed using these digits 1, 3, and 8. So the table helps us to keep track and keep our data organized. Otherwise, you might miss out on one of these possible 2-digit numbers. Okay, another way for us to keep our information organized is to use a tree diagram. And these are very helpful when you have a multi-stage experiment. So for example, a true-false test consists of 10 questions. Draw a tree diagram to show the number of ways to answer the first 3 questions. So if you need to, we're taking this test and you can either answer true or false. There's 10 questions and we're only interested in the first 3 questions. So for question 1, a person can either answer true or they can answer false. Okay. So let's say that this person answered true for question number 1. Now for question number 2, what are the choices there? It's still going to be true or false. But if that person answered false, then they can still either answer true or false for question number 2. And so if we follow along this little tree here, let's say a person answered true, and then the second question they answered true. For the third question, they're either going to answer true or false. So for the third question, they can answer true or false. Or the person could have said true for the first question, false for the second, and then for the third, they can either say true or false. And so if we look at the number of outcomes, it's going to be these last branches of the tree. So here we're going to have true. One possible outcome is that the person answered true on all 3 questions. Another one is that they said true, true, false. That would be another outcome. Or it could have been true, false, true, or true, false, false. Or they could have started with false, true, true, false, true, false, 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 true, or false, false, false. So these are all the possible outcomes on how they could have answered those 3 questions. So there's 1, 2, 3, 4, 5, 6, 7, 8 possible outcomes. Okay, so this is using a tree diagram. So let's look at a different problem. So how many possible outcomes are there if 2 dice, let's say one is red, one is white, are tossed? Well, the red die could be a 1 and the white die could be a 1. The red one could be a 1 and the white one could be a 2. And if we list all the possible outcomes, we end up with 36. Okay, so we have 6 times 6 would be 36. So sometimes listing them is not going to be practical. So what we could do is we take the outcomes of the red die. So the outcomes of the red die are 1, 2, 3, 4, 5, 6. So we have a 6. The outcomes of a white die. So we look at the white die, we still have 1, 2, 3, 4, 5, 6. So the white one has 6. If we multiply these outcomes, 6 times 6 would give us that 36. Okay, so one way is to list them, like I did here. The second way is to take the number of outcomes of the first die times the number of outcomes of the second die, and we still end up with the same number of outcomes. The counting principle. So this method that we just did right here is what we call the counting principle. And so this is just saying that we can multiply the number of outcomes, so n1 times n2 times n3, to give us the possible outcomes of E. So let's look at an example here. In a horse racing, betting on a trifecta refers to choosing the exact order of the first 3 horses across the finish line. If there are 8 horses in a race, how many trifectas are possible, assuming that there's no ties? Okay, so any horse can be first. So in your first position, you have 8 options. Since a horse cannot finish first and second at the same time, now for the second position, that one is only going to be 7 possible horses, and then your third position would be 6. So if we multiply these 3 positions here, we can end up with 336 possible trifectas. Okay, so let's continue. So here's an example, counting with and without replacement. So from the letters A, B, C, D, and E, how many 4-letter groups can be formed if a letter can be used more than once? Okay, so because each letter can be repeated, we can use that more than once. We only want 4-letter groups. So in our first position, we can choose from A, B, C, D, and E. So there's 5 of them. In the second position, we can still choose from all of these. So that's going to be 5. And then from the third position, we can still use all of them. So then that's 5. And then our fourth one, we can choose from all of them again. So the number of possible 4-letter groups would be 5 times 5 times 5 times 5, which is going to be 625 possible 4-letter groups. Okay. What if we can only use the letter exactly once? So let's look at that. So we can only use it once. Then your first position, you would have a choice from A, B, C, D, E. So that's 5 choices. But let's say that you use A, then you're left with B, C, D, or E for the second position. So you would only have 4 choices. Then if you use, let's say, the letter B, then you would only be left with 3 choices for the third position. And then the last position, you would be left with 2 choices. So my answer here would be 5 times 4 times 3 times 2, which is 120. Okay, so now we're going to go into a little bit of permutations and combinations. So suppose you have 4 different colored squares and you put them in a row. This is one possibility. How many different ways are there to order the colors? Okay. And so here there are 4 choices. For the first square, there's 4 choices. Then we only have 3 left for the second square, 2 for the third, and 1 for the fourth. So by the counting principle, we would still have 4 times 3 times 2 times 1, which is 24 different arrangements for these 4 squares. So before we talk about permutations and combinations, we want to talk about factorial. So n factorial is just the product of the natural numbers from n through 1, where n is the number of objects. So if you look at this example here, you have 4 colored squares, so your n would be 4. Okay, so your n would be a 4. And then the formula for n factorial, you would start with the n. So in our example, we have 4. And then we would multiply it times n minus 1. So in our example, that would be 4 minus 1 times 4 minus 2. And you keep going until you get to 1. So 4 factorial just means that you start with 4 and you multiply down all the way to 1. So we have 4 times 3 times 2 times 1 is equal to 24. So if you had something like, let me get the pencil. Let's say 3 factorial, then you would start with 3 and you would go all the way until you get to 1. So this would be equal to 6. Okay. So that's how n factorial works. And so one of the things that we might end up happening in some of these problems is that we'll end up with 0 factorial. And so we just use, we define it to be 1. So if you ever see 0 factorial, we replace that with 1, or it's equal to 1. So let's say we have 5 factorial minus 3 factorial. So for 5 factorial, we're going to start with 5, and then we multiply all the way to 1 going down. So 5 times 4 times 3 times 2 times 1. So that would be your 5 factorial. And then 3 factorial would be 3 times 2 times 1. So it would look something like this. So 5 factorial is 5 times 4 times 3 times 2 times 1 minus 3 factorial is 3 times 2 times 1. So if we multiply 5 times 4 times 3 times 2 times 1, we get 120. And 3 times 2 times 1 would give us 6. So if we subtract, we get 114. And then the same for letter B. You want to deal with 9 factorial first. So that would be 9 times 8 times 7 times 6 all the way to 1. And then 6 factorial would be 6 times 5 times 4 all the way to 1. So it's going to look something like this. So we have 9 factorial is 9 times 8 times 7. And then notice here that it has 6 factorial. And this is just a shortcut because if you notice here, 9 factorial, if we just wrote it out, that is 9 times 8 times 7 times 6 all the way to the number 1. Times 2 and then times 1. And if we divide this by 6 factorial, then notice what happens here. So let me just write them out. Times 3 all the way to 1. Okay, so what happens is now we can see that the 6 divided by 6 is 1, 5 divided by 5 is 1, and this is the case for all of these numbers. So the only thing that's left is these right here. So instead of writing everything out, this is one way that we can kind of save some time. So from 6 to 1, this is the same as 6 factorial. And so since we're dividing by 6 factorial, I can stop here because 6 factorial divided by 6 factorial is going to be 1. So my answer is 9 times 8 times 7, which is 504. Okay. But if you want to write all the way to 1, then that's perfectly fine as well. So permutations. So for a permutation, determining the number of possible ordered arrangements. Okay, so this word here, ordered, is important, of a group of objects. And so A permutation is just an arrangement of objects in a definite order. And so I'm going to highlight that order is important. That's how you can distinguish between a permutation and a combination, okay, is the order. So there is a formula for this. If you want to figure out the number of permutations of n distinct objects selected k at a time, then this is a formula that we would use. So P stands for permutation, n is the number of objects, and k is how many you're selecting. Okay, and so that's going to be equal to n factorial divided by n minus k factorial. So here's an example. A university tennis team consists of 6 players who are ranked from 1 through 6. If a tennis coach has 10 players from which to choose, how many different ranked tennis teams can the coach select? So one of the decisions that you have to make is if you're working with a permutation or a combination. And so you want to ask yourself, in this problem, is order important? Since it says that it's a ranked tennis team, then if you're ranked number 1 versus ranked number 4, that is going to be important, right? So, so the order of the position is important. And so here we're going to have a permutation. So the number of objects in this case is how many players we have total. We have 10 players, so we would put our 10 for the number of players we have. And how many do we need to select? We're looking for a team that consists of 6 players. So from the 10 players, we only need to get 6. And so the permutation would be P parentheses 10, 6. And if we work it out, we get 10 factorial divided by 10 minus 6 factorial. And if we evaluate this, 10 minus 6 factorial is 4 factorial. So for 10 factorial, I can write it as 10 times 9 times 8 times 7 times 6 times 5. And since I'm dividing by 4 factorial, I'm just going to write this as 4 factorial divided by 4 factorial. And so that makes the 4 factorial and the 4 factorial is equal to 1. And so all we have left is 10, 9, 8, 7, 6, and 5. If we multiply that out, then this is the number of possible tennis teams. Now, another way to do this permutation without having to go through all of this formula is that, let me get my pencil out again. So whenever you see P of, we have 10, 6, because these are going to cancel, then this number here, we would just use it to multiply down 6 numbers. So we would get 10 times 9 times 8 times 7 times 6 times 5. So you notice that's 1, 2, 3, 4, 5, 6. And so that would kind of save you some time from doing all of this. But if you're into like, I need to make sure I use the formula, then you can still do the formula. But if you had something like, let's say 4 and 3, then here we would end up with 4 times 3 times 2, 24. Okay, so that's just one way to do those permutations. So for the next one, we have 5 women and 4 men are to be seated in a row of 9 chairs. How many different seating arrangements are possible? So For A, there's no restrictions on the seating arrangements. And so here we have, so if you have a seating arrangements, then you have an order. And so this is going to be a permutation. There's no restrictions. So we have 9 people to choose from. We have 5 women and 4 men. So there's a total of 9 people. We have 5 women and 4 men. So there's a total of 9 people. And we want to select 9 of them, right? So you're trying to seat these people in some type of order. And so if we do the work here, then we're going to have 9 factorial divided by 9 minus 9. And so we get 9 factorial divided by 0. And so 0 factorial, remember what we mentioned last time, that's going to be, oops, let me see, I lost my screen. Oh, there it is. So last time we said that 0 factorial is the same as, remember 0 factorial is the same as 1. Okay. So we end up with 9 factorial. If you do the shortcut, then 9 and 9 just tells you to do 9 times 8 all the way to number 1. All the way to number 1. I'll just put it here. Okay, and so that comes out to this many seating arrangements. All right, let's try another one. So let me go to the next slide. Okay, so for the next one, we have how many different seating arrangements are possible if the women sit together and the men sit together. So now we're looking at something a little bit more different, right? So now the women want to sit together and the men want to sit together. And so this is what we call a multi-stage experiment. So the permutation formula counting principles will be used. And so if we look at this, oops, let me go back. And let me get a pencil. So if we look at the counting principle, then we have, let's look at the women first. So for the women, we would have 5 factorial, right? Because there's 5 women, we're picking 5. And then for the men, we have 4 men, so that's 4 factorial. And there's 2 ways that we can do this, right? So this is the women. This is a woman here. And then this is the men. Okay. So in this situation, the women are sitting together first, right? So like these are the 5 women. And then we have the 4 men. Okay, but is that the only way that we could have these people sitting? And so the answer is no, right? Because we could have, instead we could have the 4 men first, and then followed by the 5 women. So it could look like this. So you have the 4 men, and then the 5 women. Okay, so this is the men, and then the woman. So there's this order here, and then there's this order here. Okay, so my answer here could be that we have 2 ways, 1, 2, and so we're going to multiply it because we're using the counting principle. And then this is how we get the 5 women, and then the 4 men. Okay, so that's going to be equal to 2 times 5 times 4 times 3 times 2 times 1. That's for the 5 factorial times 4 times 3 times 2 times 1. And so this number comes out to 5,760. Okay, so that's how many ways the women can sit together and the men can sit together. Okay, let's go to the next one. So those were all permutations. And for permutation, again, the order was important. Okay, so now we're going to look at combination. So a combination is a collection of objects in which the order of objects is not important. So the 3-letter sequences ACB and BCA are different permutations, but the same combination. Okay, so this here is the same combination, but as far as permutation, the order would be important. So that's the only difference, is that the order is not important. The formula for combinations is going to be C. N is still the number of objects, and K is how many we're choosing at a time. And so notice that in this formula, you have in the top part, in the numerator, you have a permutation, and then you have K. All right, so then this, we can write it as, here's your, remember this is your permutation right here. Okay, so this is the formula, and I'm going to go ahead and we can do an example right now. So a committee of 5 is chosen from 5 mathematicians and 6 economists. How many different committees are possible if the committee must include 2 mathematicians and 3 economists? Okay. So let's go ahead and try this problem. Let me go to the next slide. Okay, so we have a committee of professors. So let's say we have 5 of them. We can call them A, B, C, D, E. And it doesn't matter if we put them as B, D, E, A, C. So choosing a committee is an example of a combination. So we don't care if A is next to B or if B is next to D. It doesn't matter as long as we have 5. So there's 5 mathematicians from whom we need to choose 2, right? Because it says that we need, let me get my pencil. We need 2 mathematicians, and we have 5 of them. Okay, so since we don't care if A is next to B or B is next to D, the order is not important. For the mathematicians, we have 5 of them, and we need to select 2. Okay, now for the economists, we have 6 of them, and we need 3. So that combination would be 6, 3. Then we're looking at the counting principle because we want to see how many combinations we have, how many ways to choose 2 mathematicians and 3 economists. Then we would take our selection of mathematicians times the selection of economists. So we need to figure out what this is. So we have C52 and C63. So for the first one, we have 5 factorial, and then we're going to have 2 factorial. The 3 factorial, where does that come from? So we want to know where this comes from. Okay, so remember that for the combination of NK, this is equal to the permutation of NK. Oops, NK. And how do we do this? Well, that's, oops, NK. And how do we do this? Well, that's N factorial divided by N minus K factorial. Okay, so in our example, our n is 5 and our k is 2. So 5 minus 2 is how we got the 3. So that's that 3 that you see here, 3 factorial. And then for 6, 3, we have 6 factorial divided by 3 factorial. And how do we get this 3 again? We're subtracting 6 minus 3 to give us that 3. And that's just coming from the formula. So now we just have to multiply it out. And so 5 factorial divided by 2 factorial times 3 factorial times 6 factorial divided by 3 factorial times 3 factorial. And we end up with 200 ways that we can make this committee. Okay. So I have 3 examples, and we're gonna work these out. We're gonna try to figure out, 1, are you working with a permutation or a combination? And then once we figure out what it is, then we'll work them out together. So the first one, a college golf course, a college golf team consists of 5 players who are ranked from 1 through 5. If a gold coach has 8 players from which to choose, how many different ranked golf teams? And I think that I'm laughing because I was like, what is a gold coach? So I don't think that should say gold. So let me try that part again. If a golf coach has 8 players from which to choose, how many different ranked golf teams can the coach select? Okay, so that's the first one. We'll call this A. Let me get the pencil. So let's say this is A. And then B is, there are 43 cars entered in the Daytona race. In how many different ways could the first, second, and third place prizes have been awarded? And then letter C, a restaurant employs 16 waiters and waitresses. In how many ways can a group of 9 waiters and waitresses be chosen for the lunch shift? Okay. So remember, permutation, the order is important. So order is important. And combination, not important. Okay, so let's look at the first one. So we have a ranked from 1 through 5, where if you're ranked 1 versus the person that's ranked 5, that is important, right? Because usually if you're ranked 1, that means you are the number 1 player. But if they rank you 5th, that's not the same. So yes, so this is going to be a permutation. So I'm going to put a P here for permutation. And then the same here for the cars. They have a first, second, and third place. So the way they finish is important. So that's going to be a permutation as well. And then the last one, you have 16, you need to, a restaurant employs 16 waiters and waitresses. In how many ways can a group of 9 waiters and waitresses be chosen for lunch shift? So here, it doesn't really matter if waiter number 1 stands to waiter number 3. The order does not matter as long as we have our 9 waiters and waitresses for the lunch shift, right? So this is going to be a combination. Okay, so again, the order is important for a permutation, but not important for a combination. So here I set these up for us already. So the first one, the first number 8, remember this is n, that's how many total objects you have. And so here it tells us that we have 8 players, so that's why we use 8. Then the next number is how many you are going to choose, and the team consists of 5 players, so that's where the 5 is going to be. So this right here is the same as 8 factorial divided by 8 minus 5 factorial. So we keep working it out. 8 factorial divided by 3 factorial. And then, of course, you know, you can write it out. 8 times 7 times 6 times 5 times 4 times, I'm going to write 3 factorial divided by 3 factorial. And so by doing it this way, then I know that 3 factorial divided by 3 factorial is 1. And so I'm just left with 8 times 7 times 6 times 5 times 4. And I think this is 6,000. Let me double check this. Let me use my calculator. 8 times 7 times 6 times 5 times 4. 6,720 ways that the coach can select the team. Okay. Again, if you wanted to use a shortcut, since you have a 5, you could just do 5 numbers here. 1, 2, 3, 4, 5. Okay, the next one, there's 43 cars, so that's your N. And they're talking about first, second, and third, so you have 3 that you're going to choose from. So if I use the shortcut here, this would only be 43 times that you're going to choose from. So if I use the shortcut here, this would only be 43 times 42 times 41. And again, the reason is because 43 minus 3 is 40 factorial. And so that would cancel with the 40 factorial below it. So that is going to be 43 times 42 times 41 is 74,046. Okay, that's how many ways they can arrive as first, second, and third. And then the last one, you have 16 total people. So that's your N here. And we need to select 9. So that's your 9 here. Okay. So if we set it up, we have 16 factorial divided by 9 factorial times 16 minus 9 factorial. And then we would write all of that out, and that comes out to 11,440. Now, if you want to kind of work on this a little bit quicker, let me just rewrite this. We know this is a permutation. Of 16 and 9 divided by K, right? So if you do the shortcut for this permutation here, if you do the shortcut for this, then that's 16. I'm going to run out of space. Let me write it up here. So we have P of 16 and 9. So that's, let me get a different color. That's not a great color. So 16 times 15. And you would do this all the way 9 places, right? So times 13 times 12 times 11 times 10. 1, 2, 3, 4, 5, 6. Okay, and so times 9. How many is that? So 1, 2, 3, 4, 5, 6, 7, 8, 9. Let me see what happened here. 1, 2, 3, 4, 5, 6. Can it 7, 8, 9? Is that 9? I feel like I'm counting wrong. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So whatever this is, and then you would have your 9 factorial. Okay. So let me just double check it and use a calculator. 16 times 15 times 14. And some of your calculators actually have the permutation and combination in there that you can use as well. Oops. Hold on. I pressed the wrong number on the calculator. So anyways, what I wanted to say is that you can use shortcuts or the formulas. So then that's the number you get. So once you have your permutation, that is representing this up here, but then you still have to divide by 9 factorial. And this is going to give you the same answer, 11,440. Okay. So so those were permutations and combinations. And since we have a little bit of time, let me see if I can just give you like a brief introduction on probability. Okay, so let me go to, let's see, maybe we can share the whiteboard. Okay, so for probability, this is from 12.3. So there's different types of probabilities. I think I misspelled it, but okay. So you have something called theoretical. And I can't spell today. And something called empirical. Okay, so the difference between these two is that one of them is kind of like what we know from the item that we're talking about. So for example, if I tell you that we have a coin, right? Like let's say we have a coin, then what do we know about this coin? Let's say it's a fair coin. Then we know that the coin has 2 sides, right? And more importantly, we know that the sides should be a heads or a tails, okay? Unless you have my dad's nickel, that one has 2 heads. So if we wanted to find the probability of getting a heads, if you toss a coin, then the way we set this up is that in your denominator, it's going to be the total possible outcomes that you have. So you have 2 possible outcomes. So that would be a 2. Now from these 2 outcomes, how many of those are heads? Just 1. Okay, so if you flip a coin, the probability of getting a heads is a half. Okay, and this is how we write the probability of that event. Okay, Now empirical means that there's some type of experiment going to happen. Okay, so experiments. So we take a coin, same idea, okay? And we're going to toss the coin, let's say we're going to toss the coin, I don't know, 5,000 times. Okay, so you would observe how many times you're tossing this coin. And so when you want to get the probability again of getting a heads, okay, so then you want to ask their denominator. Your denominator right here is going to be the number of times that you actually tossed it. Okay, so let's say 5,000, because that's how many times we tossed it. Your numerator is going to be how many of these tosses gave you the heads. So let's say that you observe 2,600 tosses. Then the probability here from this experiment would be a little bit over 50%, right? So it would be about 0.52. Okay, so in one you're taking an experiment, and the other theoretical, it's just what you know about that side. Okay, so let's do another example. Let's say we have I forgot how to clear the board. Can somebody clear the board? Oh, thank you. Okay, so let's say that we have the following. What is the probability? What is the probability of getting a even number if you toss, or I mean if you roll a fair die. Okay, so here we want an even number. I probably could have just left it as E, but I'm going to put even number. Okay, so to get the probability here, again, your denominator is what are the total outcomes of your event, of this situation, right? Well, if you roll a die, how many possible outcomes can we have? Well, we can get a 1, a 2, a 3, a 4, a 5, or a 6. So we have 6 possible outcomes. Now the event that we're looking for is an even number. So these are my outcomes, right? 1, 2, 3, 4, 5, and 6. So in my numerator, we're going to write how many number of elements are in this event. So how many of these are even? We have 2, 4, and 6. So 3 of them are even. So the probability that you're going to get an even number would be a half. Okay. And so let's look at another one. Let's say, what if we have, what's the probability that the sum, oh, that might be hard because we don't have the picture. Let me put the picture. Let's go back to the, oh, I don't see the file anymore. Oh, here it is. Okay, let me share this so we can look at the picture. Let's see. Okay, so let's say we want to know the probability that the sum of the numbers in this of your dice when you roll them equals 8. Okay, that the sum is equal to 8. Okay, so the number in our numerator is going to be how many possible outcomes are there, right? So we know that there's 36 outcomes. So I'm going to write 36 in my denominator. Of those outcomes, of all of these outcomes, how many sum to 8? So let's look for those. So here we have 4 plus 4, that's 8. So that's one of them. 5 plus 3, that's 8. 6 and 2 is 8. 5 plus 3 is 8. And 6 and 2 is 8. So we have 1, 2, 3, 4, 5. If you're able to reduce your fraction, then you want to make sure to reduce your fraction. Okay, so the probability that the sum is 8 is 5 over 36. Now, what's the probability that the sum is not 8? Not 8. So you're still going to have 36 possible outcomes. And the ones that are not 8 are going to be what? 31. Okay, so if you notice, if you were to add 31 plus 5, you would have 36 over 36, which is 100%. This right here, we call it the complement of this one. Okay, but we're out of time, so I just wanted to give you just a little taste of a little bit of probability, and so that would be it. Thank you for joining us today, and I'll pass it back over.
Thank you, Ms. Chuka, for your wonderful presentation. We do want to remind you all about our previously recorded sessions, which are available on our YouTube playlist. Today's session will also be available on that sessions, which are available on our YouTube playlist. Today's session will also be available on that playlist later on today. Also linked is a short survey to help us improve our TVE sessions. Please take time to fill out the survey. Before you leave, I want to share the TVE sessions we will have next. Just a reminder that we will not have Happy Math Hour next week due to the holidays, but we will be back on December the 5th for our final session. Math 1332 will be covering the final exam review. Math 2412 will do the same, covering the final exam review. And today at 1 p.m., you're welcome to come and join us for the Student Success topic, which will be the EPCC Mental Health Committee. The presentation will be done by Christian Salas. Thank you all for coming in today. We hope you have a lovely weekend. If you have any questions, feel free to use the chat box or the mic. And happy holidays, guys.